Yes, Lavina, what would you like to talk about, my friend?
So many things.
Oh, good. I love that. You always have good questions. I'm sure everyone has come to rely on your questions.
So, I did 1.1 on the exercises, those were easy. 1.2 was A and B, right?
Correct.
So A and B, the fractions are throwing me off.
Gotcha. Oh, because we didn't talk about division.
Yeah.
Let's do that today. Okay, so that'll be one of the first things up.
Yeah.
What else? And so it's good we're moving this to Wednesday, I guess. What else would you like to talk about?
Then in 1.3, the exponent. Like,
Yes.
So would we be doing this with like the e to the I theta with that thing?
Yeah, let's talk about that too today then.
Okay.
How to do powers, yeah.
Okay, that, and then for 1.4, it's gonna put like, for H, guess it's the same thing. Ish,
Yes, yeah, so it is kind of the same thing.
yeah.
Yeah.
Just like separate the cube root, whatever the thing is. And for,
Yes, the square root of 3, you could pull that
Yeah.
out if you wanted, yeah, absolutely.
so for F, the absolute value and.
Yes,
That-
let's talk about that too.
Okay.
Cool. Does that sound like a good place to start? And then we
Yep.
can, awesome, cool. So, yeah, division. I want to talk about division. First, I want to do an example about the powers. What if I asked you, and this was this was written in my notes as warm up. And I had to make the exponent like disturbing to keep you from foiling it out or some insane thing like that 50 times and then do that. So this would be madness to do normally. And we all know better than to do something whack, like distribute the exponent. We would never do that in a class like this. Cool. So step 1 is convert this into polar form. So to convert into polar form, I always draw it. So I've got root 2 over 2, got root 2 over 2 down, and that's my imaginary component. So here's the number that I need to represent in polar form. Let's talk about that just a little bit. And then I can also define a few things while we talk about this. So I need the angle and this length. So this length here, the length of this is the modulus. You can think of it as the absolute value in the plane. In absolute value, it's the distance. So absolute value of a real number is just how far is it from 0. And distances are always positive. Same thing here, but we have a fancy, beautiful word for it, the modulus. And that just equals the distance to 0. And it's represented by those absolute value lines. So the absolute value or modulus of z is just good old Pythagoras. So that's just the Pythagorean theorem when they ask you to find that modulus. This thing here, the angle is called the argument of the complex number. How many ways are there to measure the angle from here? As many as you want, infinitely many, right? So I could go, what would you say that angle was? Beautiful, thank you. Yeah, this is a right triangle with same sides of the same length. So this is just pi over 4, negative in fact, because we moved clockwise. But that's not the only number. It's just like the smallest sized one, because I could also do this. This is also completely legit to say 7 pi over 4. That's okay. Just a bigger number to mess with. And then I could just keep adding 2 pi to that, right? So this argument, we write arg of z equals the angle in polar form. And it is not unique. In fact, this argument is probably the first time you've ever seen anything like this. This is called a multi-valued function because it spits out a set, not just a single value. So this is multi-valued. That's something we don't really cover anywhere here other than complex analysis. This is going to be a big problem for us in the future. You've seen it, but like we kind of tuck it under the rug when we have something like this. When we have the square root of something and we put plus or minus in front, that's a multi-valued function, but then we go, stop, don't think about that, make it a function, or make it a function like this. So just to point that out to you, if you think about it, the argument is kind of cool. So there's a neat way to visualize this. I could say arg of z is here, and then the complex plane is right down here. So this will be, this is C right here. This is the complex plane on the ground, and then the argument is the vertical axis. So if I was going to graph the argument of every single number, well, the argument depends upon just whatever the ray is. So like if I had this number z here, I have that. The argument, let's say this is the positive reals. Right here, this is the okay, that's positive. Let's just make this the positive imaginary. So I'm going to put plus ri here. Here's negative ri. So that's just the reals times I to indicate that imaginary axis, and then this is the negative reals over here, just to kind of keep it oriented properly. But think about what happens as you take this ray. So for all the numbers here, the argument is the same. For all the complex numbers on this line, they all have the same argument more or less. And so there's going to be a stack above that of values. What is the argument there? Well, let's say it's like negative pi over 6. So then I would plot a point, and actually an entire line right underneath this of negative pi over 6. And then I could add all the multiples of pi, so add 2 pi to that, and that lifts us up to 11 pi over 6. So then like up here, there's an 11 pi over 6 coming out. And if you just think about how this rotates, what you end up with is like this spiral above it. Something like, it's gonna be here. It's kind of, it's hard to draw it. Oh, this might not. Let me make a little spiral. And then let me take out the hidden parts. And it's fucked up. Imagine just a little like spiraling thing that extends in all directions. I'll find a picture of it and send it to you. My drawing skills, I've drawn better versions of it in my notes than I'm doing today. I'll send you a cool picture of it. So that's just fun because I like drawing pictures. Some days maybe they don't go so well. That's probably more about arg than you need to know for a long while. Till like next week or something. How do we do this? So I convert this to polar form. So I can say that this is in polar form. Polar form looks like this. It's the modulus times e to the I and then some argument. That's just the generic formula for polar form. Put the length out in front, e to the I times your favorite version of the angle that represents that number. So for this one, I'm going to go for the low-hanging fruit. In polar form, this is going to turn, the thing inside here is going to turn into, how long is this line? What's the modulus? 1. Beautiful. So 1 is the modulus, e to the negative pi over 4i. And now this becomes cake, because now I just use the properties of exponents. So now this is 1 to the 100th times e to the negative power of 4I to the 100th. What do I do with that, those two numbers? Multiply. So 1 to the 100th is 1, and then this is e to the negative 25I. Hey, do me a favor, figure out where that is. What is that number? What is e to the negative 25I?
Would it be 25 pi?
Thank you. Yes, I lost a pi. You are absolutely right. Thanks. That's pretty important. Otherwise, we couldn't answer it. Spin around. Negative 25 pi times. Where do you end up? What's a full rotation? What's a full rotation? 2 pi, right? So you take out all the multiples of 2 pi.
12 rotations.
12 rotations and a half. We got 12 and a half rotations, right? Where does that land us in the plane? You land up right here, right? That's that. So there's your last half rotation. It would be this way. It's okay, we're going negatively. Ends up in the same place as positively. So we're on the negative real axis. So this is just -1 right here. So the answer is -1. Wow. Isn't that cool? It's just so powerful. And that's, you got to practice this a little bit, but you'll get it. So take something that's like WTF to beautiful cake. It's a nice cake. So Lavina, that probably helps a little bit with a couple of those things. Awesome. Any questions? Yes. Okay. Maybe. Did you say maybe not?
Yeah.
Okay. Had me up until the end there. All right. So let's talk about division. But before we talk about division, I want to talk about one other thing we can do with complex numbers that we can't do with real numbers. So if z is a plus bi, then z with a bar over it equals the conjugate of z. With a j, conjugate of z. And that's just a minus bi. Now let's draw a picture. Again, everything in this class, get a picture if you can. So this is z with a, notice I am using rectangular form here, and there's b there on the imaginary axis. Then it's just right down here, just a flip over the real axis. So here's z conjugate. What happens when I multiply these two together? So everybody take a minute here, figure that out.
Get back to the middle.
Would you elaborate more on what you mean there, Noah?
So if you add the angles together. then-
Oh, yeah, that's a neat way to think of it.
Yeah,
Oh, so Noah's like kind of looking at this, he's like polarizing things, and he's like, oh wait, so there's the arc of that, and then this arc is the opposite, and when you multiply numbers, you add their arguments. Remember, we talked about that. And so it lands you onto the real axis. That's good intuition, that's awesome geometric intuition, I love it. But where precisely?
A squared plus B
A
squared.
squared plus B squared. Does this look like anything? So notice that multiplying a complex number times its conjugate gives you if this number is not zero, a positive real number. So just notice that this is positive and real, positive and real, and not zero if z isn't zero. Because one of those two numbers will be non-zero, and when you square it, you get a positive. So this helps, this is basically the mechanism that allows us to divide. So for division, here's the process. probably seen this before, but not with complex numbers. So if I take z over w, right now I've got a complex number over complex number, and that looks weird. So what I do is I multiply, so let's say equals, multiply the top and bottom by the conjugate of the denominator. This is now a real number in the front, or underneath. And I can pull it out in front. It's 1 over the modulus of the denominator squared times z times w conjugate. So that if, let's do an example, nice solid example. So let's say I had 1 minus 2i over 3 plus 5i. And I was asked, what complex number is this? Now I made this up, I think it's gonna be pretty nasty, but that's okay. We can handle it. It's just numbers. So I'm gonna multiply top and bottom by the conjugate. Let me rewrite the whole thing again. And then multiply by 3 minus 5i, 3 minus 5i. Now the bottom is, you just get used to that, that's gonna be 9 plus 25, 34. Right, that's that squared plus that squared. So at the bottom, I've got 34. On the top, I do have to FOIL. Oh, did you say something? Sorry. Or was there something? Okay, I heard something. So you do have to FOIL for the top part. So we've got 3, and then, so remember the F and the L give you the real part in FOIL. So I usually do those first. So the L is going to be negative 10, because I got I squared, and then 2 negatives multiplied together. And then the outer is negative 6i, the inner is negative 5i. So my final answer is going to be negative 7/34 minus 11/34 I. Not the kind of thing you guess by just looking at it, right? Like it's like, oh wow, that got weird fast. Does this make sense? Labina, does that help on your questions? Let me take a look. And I kind of want to address part A of 1-2 because I think there's something subtle there that we should talk about.
Yeah.
That sounds good? Cool. Let me do something like problem 1-2A and help guide you through this. Oh shit, I'm erasing all the stuff that, are we good over there? Sorry. Yeah, okay, cool. Alrighty friends, so this is 1-2A-ish. So let's do z plus a over z minus a for a good little practice round. Now, we need to know this, that a is a real number. That means it's only going to mix with the real part of z. So we're going to want to introduce some notation. Let's say z equals c plus di. There's maybe some more, oh no, let's be more sophisticated and learn something in the process. What is the procedure to divide? What do I need to do? Multiply by the conjugate. Cool, so we're going to take z plus a over z minus a times z plus a, z minus a conjugate, and I'm just going to notate this, over z minus a conjugate, the conjugate of that entire thing. What is the conjugate of a real number? Itself. Because when you flip over the real axis, it stays on the real axis. So let's make a little note that the conjugate, how about we'll just notate it, conjugate of a real equals the real. No change. Yes, sir.
Is
No,
that
no.
plus
I'm sorry, go ahead.
conjugate, like when you multiply c minus a? Isn't that it's all 1 plus or?
Because I'm multiplying by the conjugate of the denominator.
Okay.
Does that sound good? Awesome. No, I'm glad you asked. Thank you. So let's do this out. So this is z plus a over z minus a. I'm just copying that. What is the conjugate of the numerator? And actually, hey, if you have your book with you, you don't, because you probably don't have a hard copy yet. Here's a little tip. The conjugates work nice. So if I have z plus w conjugate, that's the conjugate of the sum of the conjugates. And here's a couple properties. Conjugate of z times w equals z conjugate times w conjugate. It's lovely. Same thing works with division as well. And you can put a plus or minus here and you're still going to be okie dokie. So what's the conjugate of the numerator here, this thing?
Would be the conjugate of z minus a.
Yeah, so it's just the conjugate of z minus the conjugate of a, which is just a, because a is a real number. So make a little note here, because a is real, a conjugate equals a. And then same thing down here, thanks Lou for that, like so. Hey, could you take a minute and play with this, see what you can get? I'll take that as a yes, and I'll say thank you. Try to keep it just the z and a and not go to a plus bi form for the z and see what happens. I'll start working it too, here too, because I'm really curious actually. If you're getting something that doesn't look super pretty, you're doing it right. Sorry, bag. Sorry, Olivia. You might recognize a couple things in there. Are there any like low-hanging fruit you can recognize in the computation? Patterns? Yeah, keep working. It's cool. We'll give you a tip on, and you might want to start thinking a little bit about a plus bi form, but I think we'll talk about it as a group. I made like the necessary move to see what happens. And I'd like you to think about what is z minus its conjugate versus what is z plus its conjugate. So that's an important thing to think about because it's going to pop up a lot. Labine always asks like questions I like want to be asked, so it works out so good. remember we had notation for a couple of things too that you're gonna wanna get used to using. I'll just help you recall. So all the pertinent clues you'll need. Good time to pee. Not here. I'll be right back. You got it, Lou, you think? Let me take a look.
I was looking at stuff, like, I don't wanna use A and B again, because we've already got it here.
Yeah.
There's.
So I would use
Yeah.
the re and the M. That's the helpful, but yeah. Well, let's take a look at this together, just to, your brain's been wrapping around it, so. Really important fact here, if Z is A plus BI, what is Z plus its conjugate then? In terms of A and B? 2A, which is twice the real part of Z. So it's just, it means the same thing, it's just you don't, this doesn't require that you've established Z is A plus BI, it's more generic. What is Z minus its conjugate? What? 2B, yes, 2B, 2BI. Yes, 2BI, yes.
Okay, good.
Yes. And that is, it's an imaginary, so it's twice. So remember, this imaginary function spits out a real number. So this is 2m of z I. And we're just practicing. This is like all new. It's like it's just algebra you've done for your whole lives, but it's really souped up. And we just got to get used to some new conventions. So that when I come over here, is this cool with everybody how I got to this place? Let me stop. Yeah, we're good getting up to there. Okay, awesome. So then I've got modulus of z squared minus a. Z minus z conjugate is 2 imaginary part of z, I, minus a squared. Notice here that this is going to be an imaginary number, and this are going to combine into the real part of it, but we'll do that on the next step. And then I divide by mod z squared minus a 2 real part of z plus a squared. And then notice there's no i's in the bottom, right? This is actually a real number. What would be one concern with that bottom? What could be a concern of ours? Yeah, right? It's like, God, it looks so complicated. How do we know it's not 0? So I'm going to prove that in a minute. I promise you, as long as z isn't 0, that isn't 0, now prove that. I need one result that we'll have to get to in a minute. But I guarantee you, this is non-zero. So let's just make a note. This is not equal to 0 if z is not 0. So that's cool. So this is just a real number. So the final answer here is going to be this madness. 1 over z squared minus 2a re z plus a squared. That's just a scalar. I'm just going to put it out in front. And then I've got this complex number mod z squared minus a squared. That's the real part. Minus 2a imaginary part of z I. So that's what I'm looking for in that problem. And you have the minus and the plus, so it should end up looking something like that in the end. Yeah.
That's reassuring.
What's that?
That's reassuring.
It's hard to tell sometimes if you're in sarcastic mode or not, but I think it's almost always sarcasm.
That's correct.
Yes.
Been with me long enough, Dr. T.
You could have said, oh no, I'm never sarcastic, and that would have worked too.
I don't want to lie to you, Dr. T.
I know you won't. All right, let's see. So, I think that I addressed the issues, Lavina, that you were asking about. Did I?
I think so too.
Yeah. And we can talk more on Monday, because this isn't due till the start of class on Wednesday. Like, psych! Okay, so to prove to you that this is not 0, you're actually going to see kind of in the proof of something else that is the case. So let's take a look at that. We have,
Also, A.
yes, sir. Yes.
Could be negative, A could be Z.
No, A can't be Z because A's a
Ass-
Z could be yeah.
Assuming that does not.
That's an excellent point. Good eye. Z cannot be A. Yeah. Because what would happen if Z was A? If Z was A, then this would be A squared. This would be minus 2A squared, because the real part of Z is just A then, plus A squared, and oh yeah, that would be bad. We would get a 0. Awesome, Noah. Solid. Great job. All right, so hey, let me ask you this. Do we have a what's the formula for this? Can you simplify this for me? What does that turn into? What complex number is 1 over a complex number? And it's division. We have a division problem, right? Top number is 1, bottom number is Z. So what is the division rule? How do we do this? Yeah. So I take this and I multiply by the conjugate. What's the denominator? Z mod Z squared, yeah. And then the top's just Z bar. So it's actually 1 over the modulus squared, and we better not have Z equal to 0. We know that, we can't divide by 0. Times Z bar. A little later on, we'll learn a really cool way to understand that geometrically, what just happened. But I'll tell you what we've kind of done, just to give you hints of this so that when it comes later, it's less upsetting. If this is the complex plane, and this is the unit circle in the complex plane, and I take Z inside here, then what I'm essentially doing is flipping it, so the conjugate would flip it over, right? So here's Z conjugate. and then I scale it by 1 over its magnitude. Now let's think about this. The magnitude of the stuff inside here is less than 1. What happens when you divide by a number that's less than 1? You get a big number that's more than 1. So it takes this number and then scales it outside the circle. So this gets flipped out to here. The closer it is to 0, the further out it gets flipped. If you're on the circle, you don't move at all because your magnitude is 1, and you just do the conjugate thing. So like if this was z, then 1 over z would just be z conjugate. But what happens then is that this thing out here turns into that, and vice versa, right? Like this thing out here would turn into this. They flip over the circle. So you can think of this as turning the complex plane inside out and pivoting around the unit circle. So imagine I could just grab 0 and make a little hole here. I can make a tiny little hole here, and I start stretching. And I start stretching, and I pull it out, and I rip it apart, and I pull all the stuff that's inside out to infinity. So I move this little circle out to infinity. And then at the same time, the stuff that's already out infinity pivots around the circle. Think of it as a wire hoop. All the stuff that was infinity gets sucked into the circle, and this becomes infinity right here. And 0 is on the outside. First time we got to draw infinity. Oh, I had it in the inner. But now it's serious. Okay, so just be dropping little hints like that here and there. Let's talk about one of our vital inequalities for this class. And it'll help you see this not being 0 over here, too. Oh, I'm so fucking hungry, sorry. It's like I haven't eaten since like 8. I just gotta eat like a few cashews, I'm sorry. Let's do this. So what I want to show you is yuck, table nut. So this is called the triangle inequality. Sorry, I'm talking with food in my mouth, but I'm gonna black out otherwise. I'm like a vole. I get constantly, like my friends constantly make fun of me because when we play video games together, I have to go get snacks like every 20 minutes. Voles have to eat to live. If they stop eating, they die. So, very much like that. Triangle inequality. Z1 and Z2 are complex numbers. That's an element of C there. I want to look at the modulus of Z1 plus Z2 squared. How could I find the modulus squared? What's the way to find the modulus squared of a complex number? If I want this, what do I do?
Is this supposed to be Z1 and plus?
It sure is. Yeah, thanks.
Okay.
Yeah, good call. Yes, ma'am. What's the computation for this? Oh wait, say that again, Nathan.
I thought it was W times W.
It is, yeah, absolutely, yeah. W conjugate, absolutely. So we'll rewrite this like that. So these things like the conjugate of the sum is the sum of the conjugates, those are things that you should catch. Definitely do the reading because I won't hit all those little details in here. But I will apply them. So now the conjugate of the sum is the sum of the conjugates. It's a fun computation to do. I don't think this class exists without FOIL. What's FOIL? So we got Z1 conjugate. And you could say Z bar too. That's also a completely legit lingo. So that's first, then outer, the inner, and last. And then we see two things that are pretty obvious right off the bat, I hope. They've become a little more obvious. What are some immediate simplifications I could make in this computation with just different notation?
Z1 squared instead of Z1 bar.
Love it.
And the same thing with Z2 squared.
Yes, ma'am, absolutely. I'm gonna leave space here because I'm gonna do something funky. Good job, Sydney, thank you. Remember how I said that the conjugate of a product is the product of the conjugates? That was one of the rules. What do you think the conjugate of the conjugate is?
The original?
The original. All right, I'm going to use these two facts right here. That doing the conjugate twice takes you back to where you started. So inside here, I'm going to notice that this thing is actually the conjugate of this thing. Right, so this is Z1, Z2 bar plus Z1, and I'm also using the commutative property of multiplication, which also holds for the complex numbers. Check that out and contemplate what just happened. The conjugate of this thing, that conjugate goes to, oh wait, I fucked it up. No, I didn't, no, it's fine, no, I didn't, no, it's okay, it's okay. Yeah. So this is Z1 conjugate, that goes there, and then this double conjugate takes you back to Z2. So this guy right here is the same as that. Make sure you see that, please. So fat. Does that look okay? Does that make sense? Sydney, you're like kind of making faces, that's why I'm.
Just say it again, but slower.
Yeah. So, look at this thing here, just focus here. So to take the conjugate of this product, I would take the conjugate to each piece, so Z1 becomes Z1 bar, times Z2, which already had a bar, now it gets a new bar.
Oh, okay.
Do you see? And then that's just this thing here. That's just where I started. Does that make sense?
Yeah.
Yeah. So it's a funny little manipulation. But why would I even care about making this plus? Why would I care about that? What can I do with these now? These become what? Notational.
You could do the mod squared of both of them.
I can only do mod squared, Louis, if it's the same thing times its conjugate, because we don't know that they're the same necessarily.
Yeah.
But what happened when we took a number and added it to its conjugate? What did we get? Let's use lingo of real and imaginary parts. Too real, there we go, beautiful. So when you add a number to its conjugate, and let me go with what Labina was saying. If I add a number to its conjugate, I just get twice the real part. So I'm going to notate this here. This is just two real Z1, Z2 conj. And so let's rewrite this whole thing. So this now is Z1 squared plus 2 real part of Z1, Z2 conjugate plus Z2 squared. Now we're almost done. Make sure you're caught up. I'm gonna clear this up over here. So let's just, we need this fact. That if I take the real part of an imaginary number, that is less than or equal to its modulus. Let's see why that's true. Here's W. Here's the real part of W right here. Here's the modulus of W right here. So real part of W is this length. So the side of a triangle is always less than or equal to the hypotenuse length. Otherwise you have some kind of weird geometry going on. Right, so both of these sides are less than or equal to in length than that hypotenuse. So the real part, so right now I'm assuming it's positive. I could have said it was negative, like this, and it holds even more. So now the real part of W is a negative number. That's definitely less than this dude. So this holds true for all W in the complex plane. We have less than or equal to. Olivia, is there something you want to talk about over here?
So you take the conjugate of.
Wait, okay, so I just want to look at where you're looking. Are we, we're not looking over here?
No, no.
Oh, good, because we'll get
So
rid of
you
this.
go like you take Z2 and bar Z1, and you go, where did,
So do you want me to walk this through real quick again?
yeah,
Yeah, no problem. So, to move from this to here, kind of think it backwards. The conjugate of a product is the product of the conjugates. So this big bar can be distributed to Z1, so that would make that Z1 bar, which is this guy.
okay,
And then when I bring the bar, the big bar down to this Z2, which already had a bar, it's like conjugate of the conjugate of Z2, which
Didn't
is
Z1
Z2.
have the bar?
Say that again?
Didn't Z1 have the bar?
It does, yes. So Z1 has the bar here, and then I just shared it, I moved it up to share it over the whole thing.
Okay,
And the Z2 already had a little bar, or I added a little bar to the Z2. So basically, here's what I did. I took this thing and go, oh, I'm gonna put a bar here, but then to get back, I have to,
oh, okay,
that's what it, maybe that's a better way to see it.
yeah,
It seems like it was.
yeah,
Awesome. Does that sound good now?
yeah.
Awesome. So I need that fact. Because now I'm gonna go, oh shit, look at this. This is less than or equal to the modulus of Z1 squared plus 2 times the modulus of Z1, Z2 conjugate. I'm taking this. That's where the less than or equal to comes from as I apply this property here. Let's call this star. I'm applying star to this middle piece and saying this is less than or equal to this. And then I'm just copying these other two pieces down. We're learning so much. This is such a great proof because we have to think about so many subtle things, so many subtleties.
There's so many Z's happening right now.
There's a shitload of Z's.
Yeah, sure are.
Yeah.
Yeah, hold
I messed up somewhere.
on. Was it in the subscripts?
Yeah.
Excellent.
Where was it?
So, you tell me.
Can't tell you much.
Oh, you've already told me several awesome things today. How do you think the modulus of a product relates to the product of the moduli?
It's,
The same.
yeah, it's the same.
It's, yeah, you just
We've
multiply
said that
it
in other
together,
words before.
right? Yeah. And think polar form. If I have r e to the I theta times another q e, I'll try to solve it as an own subterm, phi I, like that. When you multiply these together, you just get rq, that's your new modulus, e to the I theta plus phi. You add the arguments. Sydney, yes ma'am.
Okay, just for clarification
Please.
purposes, in that, so when you go on that little line, you say by star, what exactly goes before the less than or equal? Is it that whole expression?
This entire expression, so you could just copy this underneath. This would be,
Okay,
this entire thing is less than or equal to this.
okay,
Yeah, thanks.
Heard.
Yeah, thank you. It's helpful. Other clarifications or questions? Let's just make sure we're all, like on the hike, we haven't lost anybody, right? Like when you're hiking, you always have someone in the front and the back. Make sure nobody gets lost. I'll be the person in the front and the person in the back. All right, let me ask you another question. Cool, so this is good. So the modulus of the product, and this is in the book, read the book. So this is just equal to, that once this is introduced, the whole thing will become a less than or equal to. Once you introduce an inequality in a stream of computations, that stays. So I'm saying that this is equal to the following, but this thing here will still be less than or equal to that original thing. So this is going to be z1, z2 squared plus 2 mod z1 times mod z2 bar plus z2 squared. We're almost there. We're really almost there. How does the modulus of the conjugate relate to the modulus of the original? Take this thing, here's z, Does it change the length? So modulus, here's the modulus of z. Is this the same length, the modulus of z conjugate? Yeah, because it just flipped, right? You didn't change anything, it's just a perfect flip. So this is equal to mod z2. It's just the modulus of z2, we're just about done. So this is equal to, and you should be recognizing this product here as a good old friend. Who squared is that?
Z1 plus Z2.
Oh,
Oh shit, yeah. Oh shit. Let's summarize what just happened.
Yes.
So like, you don't need to know how to do this computation to succeed in this course.
Okay.
But being with me on the journey is essential because there was lots of things we talked about. So, thus, oh, I haven't written that in a long time. That feels good.
So much joy.
Ah. Thus, z1 plus z2 squared is less than or equal to modulus z1 plus modulus of z2 quantity squared. And I'm going to take the square root of each side. And since the square root, the positive square root, is an increasing function, I can do this. So I just want to say that for the camera in case anybody's watching and wants to bust me on it. One of the people who watch my videos that I don't know.
Nice.
Triangle inequality. What does the triangle inequality say geometrically? Here's Z1. Here's Z2. Ooh, I'm gonna pop a Z in there. Popping Zs. So we've got the Z's there. This is the modulus of Z1. This is the modulus of Z2. What does the sum of Z1 and Z2 look like relative to this shape?
Parallelogram.
And so this is Z1 plus Z2 right up here at that corner of the parallelogram. And again, it's just back to the triangle, right? I've got this triangle. This side has length Z1. This side has length Z2 because it's the same as that side. And so this has length Z1 plus 2. So the hypotenuse of a triangle is always bigger than or equal to either of the sides. Could have said that, but it wouldn't have been as fun. We could have taken the tram to the top of the mountain. Like down in Glenwood, right? Like ride up the mountain. We walk up the mountain. All right, triangle inequality. This will be vital in this course. And there's a little subsidiary, a corollary that I just want to easily pop out and be done with. What time? We started at 11, right?
yeah.
Okay, cool. So corollary. And the corollary is that I know how to get there by proof, then I never remember what it actually is. Okay, so the corollary is this, and then we'll prove it. Mod Z1 minus Z2, the absolute value of the difference of the mods is less than or equal to the mod of the difference. The sum like this, yes. I'll just write it out. It's easier to just write out and prove. So let me write this up, and then let me say, what? Why? So check this out. This gives me an upper bound. So the triangle inequality allows me to upper bound this sum. So allows, why are we doing this? Allows us to give an upper bound. And that's going to be an important way to think of it on Z1 plus Z2. Just knowing the magnitudes of Z1 and Z2. This gives me a lower bound on that quantity, Sydney.
Is that absolute value or mod on the second part?
That is, what an awesome question. Oh, I love that. After I take the mod, this becomes real. This becomes real. So this is actually an absolute value over here.
Cool.
You're right. But you can just think of it as mod too. Like in this, yeah, but what? Oh man. Awesome insight. Really exciting. So let's just do a quick little proof. Oh, the modulus of z1 is equal to the modulus of z1 plus z2 minus z2.
I love that.
Right? You've seen that trick before. Add it in, subtract it off, create something from nothing. Triangle inequality. Triangle inequality, you might want to think of it like this. Something plus something else is less than or equal to the modulus of those somethings. It doesn't just have to be a single thing, it could just be a quantity. So like in this box, I'm going to put z1 plus z2. And in this box, I'm going to put negative z2. And apply the triangle inequality like z1 plus z2 is this first part, and it's going to go right here. z1 plus z2. And then over here, negative z2. So this is less than or equal to mod z1 plus z2 plus modulus of negative z2. That is the triangle inequality applied. What's the modulus? What do you think the difference between, so actually let's talk about it. This is z. Where's negative z? We know the conjugate is down here, but where's negative z in the complex plane?
Would it just be flipped across the origin?
Absolutely. So like if this is 1 plus I, negative that is negative 1 minus I. So it just literally, just like in the real plane, it flips you across 0. So this guy here just moves across, and here's negative z, it's just on the other side. How do their moduli relate? What's the modulus of this versus this?
Same.
Yep. Doesn't change. Doesn't scale anything. So this is equal to, we're about done. We're gonna like poof on the other part of this. Not a proof. This is a proof, you get half a proof. And then we're gonna hand wave. So now check this out. If I subtract this from both sides, so we have mod z1 minus mod z2 less than or equal to the sum, the mod of the sum. That's not quite what I have up there though, right? I've got like that absolute value, and I don't have that here. Any ideas how we could maybe reverse these two? How could we show this, let's say so, and also left to the reader? How could I show this? What would I do? And maybe if I do this, this will help give you a clue.
Luke, could you just like do that first half, but start with z2, mod z2?
Exactly. Flip the 1s and 2s around. So start with z2 here, add z1 minus z1, then you get z2 plus z1, this becomes a z1. So this is just flip the z1 and z2 roles. And so you can get that then. And this right over here says that this quantity or its opposite is less than or equal to this. That means its magnitude, one of these two quantities is going to be positive, and it's going to equal, hence, I haven't been that long time either, that's fun. And the absolute value of this quantity is less than or equal to that, and there we go. And this helps us find lower bounds on that beast right there. Some of the stuff we'll do in here will be a little bit painful like that, but that's okay. So friends, you don't need to know how to derive those. I would just have those in your notes and know that when you need to establish bounds, this is what you're gonna do. I don't think there's any homework problems I don't think I signed anything like this. Labina, you've probably gone through all of them, is that true?
The last two I haven't checked.
What were those last two? Let's take a look, because
1.9 and 1.11.
awesome, I wanna talk about those. Cool. And then we'll call it a day. Anything here before I erase to clear up? No? Okay. Hope you come back on Monday. Please come back.
Bye-bye.
There's alternatives, we can put you in a different class.
You assume I'm taking this class because I need to take it?
Same.
Is it required for anything? I thought it wasn't.
Fun.
I have all the math requirements I need, I think.
You don't need this class for anything,
No.
except grad school maybe.
Yeah,
I just need
sometimes
this
I'll
class to
finish.
graduate. I just need a different schedule.
Gotcha.
That's not the only reason
That's
I
heartwarming.
joined this class.
It's very heartwarming.
I joined this class because I love you so much.
I have
You're my
genuine
favorite.
interest in the subject,
That's the right answer.
Yeah.
so I'll be back.
Yeah. Beautiful, beautiful. I hope
Sydney, who knows?
she'll be back. She wants to graduate.
I wanna get out of here.
All right, let's see, shit, okay, 1.9. So, fun fact, that if I have an equation like this, and I'm saying a little bit more than what the book says, because they don't wanna like upset anybody yet.
Yeah.
We're gonna be upset, things are gonna be upset. That the quadratic formula holds even if A, B, and C are complex numbers.
A word.
So Z is 1/2, or we could put 1 over 2A, negative B plus or minus square root. You don't usually see it written like this, but same thing. That holds for all numbers. That's beautiful. In problem 1.9, and I kind of want to lead you down the start of this, and then let you kind of have them find the magic, but I want to give you some pointers on it, because I love problem 1.9. So problem 1.9, problem 1.8 is easy. Use the formula. Nothing weird will happen in 1.8. Something very weird will happen in 1.9. Cool. Yeah, absolutely cool. Freaking awesome. Something weird better happen. Otherwise, why are we here? We're explorers, right? So 1.9 looks like that. So blindly apply the formula. That's my first tip, and let's just do that together. So we're gonna get Z equals, so A is 1, so I've got 1/2, B is 2, plus or minus, and I'm gonna have square root. B squared is 4 minus 4 times 1 times 1 minus I. Hey, take a minute and simplify that. Let's just do it. Let's get some of your homework done while we're here together. You're going to see something that hopefully is a showstopper. And it's kind of a cool way to introduce you to this idea. Oh shit, I got something else I want to show you too. Just thought of it. I can write it down. Yeah, yes, yeah.
Doesn't know how to go with it.
Yeah, I know, but it looks cool, right?
Yeah.
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 Yeah, yes,
Yeah.
yes,
Yeah.
yeah.
It was affirmative.
That's good. There's no room for middling attitudes in this class. All right, so, let's see here. Oh, you just got, yeah, I'll put up here what it turns out, and let's see if we need to talk about why that's so. That's what you got right now?
Yes.
Yes. Yay! The square root of I. This is like our first toe stepping into the weirdness of complex analysis. You're gonna be able to take square root of anything by the end of this class. You're gonna be able to take any root you want of anything you want. We haven't quite talked about a methodology for this, right? But so let's say that z is equal to the square root of I. Let's think this through together. So I'm looking for a number, z, whose square is I. What is the polar form of I? So here's I. What's its polar form? What's its modulus? 1. What's the angle? 9 degrees, but? Pi over 2. So this is actually, I'm looking for a number whose square is that number. So I need to find some number that when I multiply it by itself, it gets me there. Think about, and I don't want to tell too much, but think about polar form. How do you multiply numbers in polar form? What do you do with their angles? And think about, I'm going to leave this right here. And we'll talk about it more on Monday, but please, hurt yourself on this.
Cool.
Yeah, hurt yourself on this. This is good. You need this pain. This is good freaking pain. But I want to talk about this before we call it a day, because this is just pretty weird and one of my favorite math facts of all time that you never get to see until here. I'm going to raise both sides to the ith power, whatever that means. What do you do with exponents when you do this? Do you add them or multiply them? Multiply. So I to the ith power is e to the pi over 2 I squared. I to the I is what? E to the negative pi over 2. It's a real number. And it involves e and pi. That's like, you know this one, right?
No,
What?
unfortunately.
No.
Does that
No,
dot
what?
mean something?
It's like, it's weird. Yeah, it's hard to hear Sydney. It sounds like she's saying derogatory things, so it's muddled.
Usually am.
Does that dot mean something, or is it like
That dot,
The
no,
one
like
above the 0.
above 0?
no. That's a new 0 that we'll talk about on Monday. No.
Oh, this is,
Are we doing?
She was really concerned.
Yes.
All right, I'll be in my office 11 to 12 on Friday if you need anything, but reach out by email otherwise.
I've been,
I'll show up. I'll show up.
Okay, cool.
in physics
I'm
class,
crying.
it was going to give me dot
That's funny.
derivatives and driving mad. I was sorry.
I don't even know what that is.
It was when Newton made calculus, his derivatives were just to write a dot as a variable.
Oh, I like that because you're using t, right?
Yeah, we're using R.
But I mean the independent variable's t.
Yes.
So, yeah, that's the time. I like.
I know.
Yeah, so only
I-
my
You know,
next
just
class,
use,
next
what's his name?
No,
It's better. You wanna, why are we even pretending?
Because Newton had the bucks. And so Newton took Newton had the political power.
You altered the big tantrum and now we all respect him. It's not how it should